Sure.
I just noticed that my exam 2 isn't in the grade book.
Oh, I haven't graded them all yet.
Oh, you haven't? Okay,
Working
I
on
just
it.
was wondering because.
Working on it.
Yeah.
But it should be there soon.
Okay, sounds good.
Hey, Drew.
So when I did it, for the hourly, I'm just. Oh, okay. Okay. Thanks, Jack.
Under the radar.
Okay.
Okay, so I've got quite a few handouts. I'll just start. So as I'm handing stuff out, we have a few files today that we'll be working on for each concept. So just the usual PowerPoint, but then one practice for independent t-test, one practice for dependent t-test, and then we've looked at correlations, but we didn't talk about how to calculate the probability. So out of 0.05, so there's a practice that we'll be doing for that. And then if we get to it, probably ANOVA as well. So just materials for today. The other two items that I'm going around with, the bottom two items there are things that I'm going to give you. So you'll have those in hand. Bottom here, this is the F table. Carson, the F table. Okay. And I'm assuming everyone still has, you still have your T table? Everyone still has their T table, okay. So I got a few extra of those. All right, so next handout going around is the ANOVA tables. Okay, very last one. This is for oral presentation, so I have one of these in hand.
All right, let me close the door.
Got that typical Montana spring type weather. My son started baseball last night, so spring is coming. So welcome. Three parts for today. First part, assess what's going on with research projects this week. Second part, talk about oral presentation. And then third part, get into Chapter 9 content for today. So first off, just with our schedule, looks like I've got, last week went really well. So, Lainey, Tommy, Jordan, proud of you. Young researchers went really, really well, I thought, for the most part. So, this week, Lainey, session 2.
Yes.
So I've got your software protocol loaded. So should be good to go there. So probably Friday morning I'll have things hooked up and calibrated, and then just like before around noon is when most people.
Yeah.
Okay.
It all came around noon, and then one girl doesn't get a class till 12:40, which isn't.
Okay. And I've got our little cheat sheet here for the
Yeah.
2 conditions. So, and then Jane, day 1, right? So, jump mat, dumbbells, whole body vibration plate, correct?
Yes.
Okay, and then what time is your first participant?
The earliest I put at noon.
Noon. Okay, so I'll either be in the lab or in my office. So just come and get you set up. Christine, also good to go for Friday. Jump mat, and I do have a meeting at 10.
Okay.
You could come by around 9 and pick up the jump mat, or come by a little before noon and pick that up.
Okay, I get out of class at 9:10, so is that like right after that? Is that okay?
Yes,
Okay.
yeah, before the meeting starts. So, okay, so good. And then we'll just keep progressing. And I'm excited for today because a lot of you, Tommy and Carson especially, you're going to be using correlations, and you want to calculate probability values. So this spreadsheet will help you with that process. Okay, so part 1 done, part 2 of class today. So wanted to give you some idea of how I'll be grading your oral presentation. So order is posted front page of D2L. So just some instructions there with people that will be presenting on each date. This is the rubric for your presentation. So you can see 6 different categories, each judged from 1 to 4. And so I'll add that up and then multiply by 2 to get your score out of 48. As far as an example goes, there's also a PowerPoint posted for that. Sample oral research presentation PowerPoint from a student that was here about 4 years ago. As far as 12 minutes goes, that can be a long time if you're not used to being up in front. My suggestion would be get some note cards. I'm not gonna mind if you have some note cards. You really need to dive in and get to know the literature. So with your introduction and background sections, that's a good way to use up some time just presenting the rationale and some of the prior literature and how your project might fit into the current body of literature. So talk about what brought you to study your topic. And then at the end of the background introduction, you present your hypothesis. The other significant time component would be your discussion. So after you present your results, we want to know how that relates to the present literature, so how that fits in. Would you do anything different? Were there other studies that were consistent or inconsistent with your results? And then talk about the reason why. So please, note cards encouraged. Dive in and really get to know a few studies, because you can talk about studies to justify your own hypothesis, and then how those studies fit in with your results. And so that'll take up some time. If you have roommates or something, practice is a good thing. Have them time to make sure you've got the time limit there. So 12 minutes, 15 minutes-ish. If you go over that, it's fine, but at least 12 minutes with your presentation. Did you have any questions? So take a look at the sample there. Yours doesn't have to be exactly like that, but it's an idea to get you started. Okay. All right, so let's dive in. We're into differences among groups. All right, so differences among groups. So we're going to talk about 3 different types of tests. So independent t-test, dependent t-test, and then ANOVA, analysis of the variance. So single factor ANOVA. Single factor ANOVA is as far as we go in this class for statistics. So I'd like you to go at least to that point, be able to run those analyses, understand what it means. So for the ANOVA part, especially just to introduce you to that, rather you'll do the steps for independent and dependent t-test, but for ANOVA, I want to start just here with the table. So just understanding what this table means, and then how to go on beyond this table if you find something significant. So for t-tests, you use the t-table, and that's table 5 in the back of your text. For ANOVA, you use the f-table, and that's table 6 in the back of your text. So you have copies of these that you can keep. Okay, so t-tests evaluate the effects of an independent variable, which is a treatment, on one dependent variable. So that's the effect or outcome. The independent variable may have different levels. Okay, so we can have different time points would be a level. You can have different conditions or different groups. So as I think about what a lot of you are studying, this would fit that description of a t-test. You have 2 groups being examined on one dependent variable, or over multiple time points, 2 time points. So just as an example, common independent variable would be exercise intensity. So exercise intensity can have multiple levels. So if it's a t-test, we're talking about just 2, right? So 50% versus 70% of a maximal heart rate. So you'd have 2 different groups that exercise at each of those intensity levels over a long period of time, and then the outcome or the effect would be the dependent variable. So looking at the effect of exercise intensity on VO2 max with 2 different conditions, 50% versus 70%. So the purpose of a statistical test is to evaluate the null hypothesis. Okay, so the null hypothesis says there are no differences. Right? So typically we use the probability level of 0.05. So what we're saying is that if there's a difference in VO2 max between 50% versus 70%, we would say that we get that difference 95 times out of 100. So 5 times out of 100, according to this probability, those results would be attributable to chance occurrence. So a statistical test is always a test of the null hypothesis. So we have 2 outcomes, really. We can reject the null hypothesis. Okay, so we can reject the null hypothesis, which means there are differences, real differences between conditions, or we can fail to reject the null hypothesis, which leaves the null hypothesis in place, right? So if we fail to reject something, that is just another way of saying we accept it. So fail to reject or accept the null hypothesis. So in previous chapters, we talked about a couple of different scenarios where we have an error in our statistical test. So 5 times out of 100, results are attributable to chance. So if we see differences between conditions, 5 times out of 100, there's not really differences. We call that a type 1 error. So we reject a true null hypothesis. Type 2 errors, on the other hand, is we fail to reject a false null. So if the null is false, meaning that there's actually differences, and we fail to reject it, then we've made a type 2 error. So we're not seeing those benefits, potential benefits, due to an error in our statistics. So I think a lot of times we rely a lot on statistics when I think that's a good place to start, but we also have to look at all the other research that's been done. We have to have good logical reasoning, good experimental design, and appropriate theorizing. So that's why we use effect size a lot of the time, because effect size doesn't rely on probability. It shows you the actual magnitude of differences. And a small magnitude of difference might be meaningful for some people, especially if you're just talking about, a 100-meter sprinter, a tenth of a second improvement may not pass the probability test, but from an effect size, that's meaningful for an elite athlete. Okay, so 2 different assumptions with this testing, statistical testing. The observations are drawn from normally distributed populations. Okay, so whatever characteristic we're monitoring, vertical jump, strength, flexibility, these are all characteristics that in a large enough group of people would be normally distributed. The second one is observations represent random samples from the population. So how many of you can honestly say with your project that you're meeting both of these assumptions? Pretty tough, right? And I can relate because most of the sports science research in the United States takes place where, do you think? Colleges, yeah. And most sports science studies, at least in the United States, are what duration, do you think, in weeks? Why is that? Semester, yeah. So other countries, it's a little bit different. The way the research is set up is different, where researchers are able to follow people over long periods of time, over several years, which I think a lot of the sports science research from the Soviet Union has been translated into English, which really provides a great resource for sports scientists here, looking at what might happen over longer periods of time, over several years. So the upside of this whole thing is, fortunately, the t-test and f-tests are very robust to common violations. So that's where we get our samples of convenience. So they're robust to potential violations of these assumptions. Okay, so let's talk about an independent t-test. There's a couple of examples, and as I look around, there's those of you that would fit in each category. So example number 1, one person compared on 2 different conditions for the same dependent variable. So as I was thinking about this, Jordan's research would be an example where a single person is compared on 2 different conditions. So Jordan, your research was internal versus external focus. Is that right? So, and each person, I'm assuming, did both conditions, yeah, so that'd be one example. So two different conditions, but every person does both of those. The other example of an independent t-test would be two different but equal samples. So this would be where you have a large group of people and you divide them into equal groups, okay, and the assumption is that at baseline they're equal on whatever characteristic you're measuring. And so you take these two equal samples and you have them tested on the same dependent variable. So that would be like Christine's research. She's taking her volleyball team, dividing them into two equal groups, and then testing them on a control versus a treatment condition. So this would be similar to what Christine is doing for vertical jump. Okay, so independent t-test. So I'm going to present equations from your textbook. So for an independent t-test, this is the equation. It's equation 9.3. So what we're doing is taking the difference between the mean of group 1 or condition 1 and subtracting the mean of group 2 or condition 2. Okay, so what we can immediately see is that you want a large difference for this result to be significant. You want a big difference between the mean of one group and the mean of another group. So you've got two groups, and each of those groups has a mean score. And so if you want to find something significant, a significant difference between those groups, there has to be a large difference between the mean of one group versus the mean of the other group. Okay. Now, that's not the only thing we have to consider. So we talked about how important the mean of a group is, but what about variability? What's our key measure of variability? Yeah, standard deviation. So not only are you taking the difference between groups, but you're also dividing by what we call the pooled standard deviation. So you're taking the standard deviation of group 1, the standard deviation of group 2, and taking the square root of that. And so if you look at, this is called the t-statistic. So you're taking the difference between means and dividing it by the pooled variability of both groups. Okay, so mathematically, to get a really high t-score, so to maximize this t-score and to increase the chance that you'll have a significant result, you want a very large difference between these two means, but you also want very little variability. So you want the standard deviations to be really small for each group. So as the variability goes down and you have a large difference between means, the t-score is going to go up. So large difference between means and then very tight variability or very tight standard deviations around each mean is what we need to get a good t-score. Okay, now before when we were doing confidence intervals, degrees of freedom was calculated how? It was just the number of people minus 1, right? Okay, so independent t-test is a little bit different. So for an independent t-test, the degrees of freedom is calculated as the number of people in each group or each sample minus 2. So that's something to remember as well, is you add both conditions, number of people in both groups, or number of observations in each condition, and then you subtract 2 to get the degrees of freedom. Okay, so at this point, I'd like to go through just a couple examples of independent t-tests. Okay, so right here. So this would be that first spreadsheet. So independent t-test practice spreadsheet. So if you look up here in the top corner, okay, this is a two-tailed test. So when we look at table 5, we're going to identify our degrees of freedom based on the two-tailed row, not the one-tailed row. So the one-tailed row is on top, everybody see that? And then the two-tailed row is right underneath that. Okay, but with an independent t-test, our degrees of freedom is just a little bit different. Okay, so remember the formula for independent t-test. It's n1 plus n2 added together, and then what? You got to subtract 2. Okay, so we have two different groups. We have sample A. So this is, Christine, this would be almost exactly what you're going to be doing. So you have sample A, vertical jump height. You have sample B, vertical jump height. And then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 observations in each group. So what's your degrees of freedom going to be? 10 plus 10 minus 2 is 18, right? Okay, so let's go ahead, look on table 5. Let's find your, for this independent t-test, let's find your critical value of t for a two-tailed test at a probability level of 0.05. So as I'm looking on table 5, I'm going down the left side, I'm going to 18, and then I'm using the two-tailed test, which is the one underneath, and I'm going to 0.05, and I'm going to see where those match up. So does everybody see 2.101? Okay, so that's the critical value of t. Critical value of t. What exactly does that mean? That means that when we calculate that t statistic, so remember that formula on that slide, m1 minus m2 divided by pooled standard deviation. In order to be significant, that t statistic has to be greater than 2.101. So when we do that calculation, if that result is greater than 2.101, we know that we have a significant result at a probability level of 0.05. Does that make sense? Yeah. Okay. All right. So let's go a little bit further here. Okay. So two different samples, one dependent variable. Okay. Now I referenced where you find this material in the textbook. Okay. Just so it's there. And then I've went through big long formula of how you would calculate this if you went through everything. So fortunately, we have Excel and other software that can do all this for us. Okay, so I wanted you to know how the formula works and the process of calculating, but fortunately, we have Excel which can do this for us. Okay, so at this point, if you'll put your cursor right here in C37, and we'll just do our automatic analysis right here. So C37, then we'll go up to data, data analysis, and so that comes up. Okay, so I'm going to have some choices here. So near the bottom, you have one choice for a dependent t-test, which is sometimes called a paired t-test. You also have a couple of different choices here for an independent t-test. So the independent t-test is described as two samples, so in other words, two groups, assuming equal variance. Okay. Or two samples assuming unequal variance. Okay. So for our purposes, we're just going to assume that these samples have equal variability, equal variance to start with. So we'll just make it simple and we'll just select t-test, two sample, assuming equal variances. So that's what you'll select to start with, two sample, assuming equal variances. And then you can click OK from there. Okay, so it's pretty straightforward in how you run this. Variable 1, variable 2. So you can click right there on that black arrow with the underline. allows you to go into your spreadsheet. Just like we've done before, you want to make sure that you highlight the rows, because that'll come up on the output and help it make more sense. So you'll just highlight these title along with all the numbers there. Okay, so then you can go back in by clicking, you can go back in just by clicking on that spot right there. Okay, and then variable 2, same thing, you'll just highlight that. So you have that in. So things are going really well. All you need to do is click on the labels, because that will make sure you include those titles for each group. You can also adjust your alpha level, so if you wanted to be just a little bit more strict with maybe like a 0.01, you could do that. And then you would want to put your output range right here. So you can go in the spreadsheet and just go down to where we were. So C37, just like that. So that's, as long as you have your data in correctly, so Christine, this would be exactly how you put in your data to get your T results. So then all you have to do is click OK, and you come out with this nice table. So this table shows you for each group, okay, sample A, sample B, you have the mean and the variance. Okay, what's the standard deviation equal to? Square root of the variance, right? Yeah. Okay, the pooled variance is right here, so remember. And then you have your degrees of freedom, which is, we already know that, it's 18. I want you to take a look here, critical value, T critical for a two-tailed test. So 2.100, but if we round it up, what would we get? Yeah, it'd be the value that you found on the table right here, so 2.101. So that's consistent. Okay, so for a two-tailed test, what we need to do is compare the calculated T statistic with the critical value. So the critical value for a two-tailed test is here, and our calculated T statistic is right here. So I'm going to highlight this. Our calculated T statistic is right there. So the formula from the slides, M1 minus M2 divided by the pooled standard deviation, we get 4.46, 4.47 if we round up. So we're comparing this value to this value down here. And so because this value, our T statistic, is greater than our critical value that we got from our table, we know that the differences between sample A and sample B are significant at a probability level of less than 0.05. And so we've actually got the exact probability there, and it's way under 0.05, way less. So this is the exact probability for a two-tailed test. So everybody okay with what we have up here? Okay. So if you'd be willing, quickly, I want you to switch spreadsheets. And let's do this independent t-test for bench press power. Okay. So let me explain how this particular study worked. So this is a case like Jordan's project, where you have one person doing two different conditions. So we have each participant, 1 through 10, doing bench throw power in watts and traditional bench press power in watts. So traditional bench press would be just like pressing up as fast as you can, but you're not letting go at the end of the range of motion. Whereas a bench throw would be coming down on your chest and then actually projecting the bar, so releasing it. So in this particular study, we used special equipment where you can actually throw the bar. How many of you have ever seen that or done that? Okay, so that's the idea. So bench throw versus traditional bench, okay, and each person did both. Okay, now what's different about this spreadsheet versus the last one? Okay, well, the last one was a two-tailed test. This current one is a one-tailed test. So explained on page 162 in your textbook, but I'll summarize. If you have a strong theoretical basis for expecting one condition to be higher than the other condition, then it's a one-tailed test. So based on what you know about biomechanics and kinesiology and strength and conditioning practice, which of these conditions, without even looking at the data, just looking at the titles, which one is probably going to result in higher power output? Bench throw, right? Okay, so if we suspect that, and there's a strong theoretical foundation for that, then that's when we use the one-tailed test, because you know one condition is probably going to be higher than the other condition. So if you kind of know the direction, then you can go with a one-tailed test. If you don't know which direction the differences are going to be between groups, then it's a two-tailed test. So in this case, it'd be a one-tailed test. So it's really a lot the same. So you just go down and let's put our analysis here in same cell, C37. So we'll go here with our data analysis. Two sample equal variances. Okay, so we'll need to, well, maybe not, if the spreadsheets are set up on the same alignment, yeah. So we can just use that. Just make sure. Okay, labels 0.05, yeah. Down there in C37. Okay, and then if you click OK, then we've got our output. So what we have here is, you see the mean of the bench throw was 319 watts. The mean of the traditional bench power was 277 watts. So then what you'd want to do, because you are saying it's a one-tailed test, you could look at your T statistic, so that's right here. There. Okay, and then you say, okay, well, what's the critical value? Okay, so critical value for a one-tailed test is going to be 1.73. Okay, so let's find that on here. So if we had the same degrees of freedom, okay, so it's still 18 because there were 20 observations, okay, there were 10 in each of those conditions, minus 2 is 18. And then if you go across, and you're looking up on top now, at the one-tailed, so if you go to 0.05 on the one-tailed row, and then down you see 1.73 there, right there. So that's where we get this number from. So then you can compare that with the probability value. So in this case, for this particular sample, was there a significant difference in this case? No, there wasn't, because this number right here, 0.26, has to be less than what to be significant? less than 0.05. And we also know that in order for something to be less than 0.05, the t-statistic has to be greater than what number? Has to be greater than the t-critical, right? Okay. All right, so everybody good. Okay. All right, so that's independent t-test. Okay, so if you have enough people, and I realize that a lot of you, it's really 3 to 5, like what we said in the course outline, but a lot of you, because you're on teams and so on, you were able to come up with enough where you could do a t-test. So how should you write the results of your t-test in your research report? So that's what we get to now. So reporting a t-test in APA format. So there's APA format for everything. You might as well, it's part of life in this field. Okay, so provided an example for you. A researcher compared high-density lipoprotein cholesterol in groups of weight trainers. What's high-density lipoprotein cholesterol? What is it? No, it's the good cholesterol. Why is it good? Well, it scavenges the bloodstream. So cholesterol is not a good thing to have in your bloodstream. So it binds to cholesterol and takes it where, do you think? Takes it to the liver. What does the liver do with it? Processes it, converts it to bile that we get rid of. So we excrete it. So it prevents the buildup of plaque in our blood vessels. So there is some good evidence, especially recently, about apple cider vinegar. How many of you have seen this on the shelves? Okay, just got me some. I read this and then I was like, I'm going out right now. Got some. Tried some this morning. Has anybody ever tried it? Yeah. So I had to put it in something in order to get it down, but I got it down, so I'm healthy. At least I think so. So, okay, so this particular study looked at weight trainers that did or did not supplement with organic apple cider vinegar. So how much did they take? 2 tablespoons a day for 8 weeks. Okay, so what were the results? Okay, so in quotes here. So the fasting high-density lipoprotein cholesterol. So whenever you have a blood test, they come in 12-hour fast. Fasting HDL cholesterol level in the supplement group was significantly higher versus the control group. So that's a good thing. So if you've ever looked on your blood test, they really like you to have HDL cholesterol right around 60 milligrams per deciliter. So there's a couple of things that are really good for that. Endurance exercise is good, but then also certain foods that you can take into your body. Isn't that interesting? You take in just this simple practice and there could be a significant difference. At least if you're looking at, have to look closely at what it just says weight trainers, but I'm sure there was some type of subject description in the study. Okay, so the fasting HDL-C level in the supplement group was significantly higher versus the control group. So this would have been a 2-tailed independent t-test, kind of like what Christine is doing, where you have a group of people, you divide them, and so you're assuming they're equal to begin with, and then one group is the treatment, one group is the control. And so a couple of things to report here. So T22 in parentheses. So 22 is the degrees of freedom. In parentheses, that's the degrees of freedom. So knowing that, how many people did we have in each group then? 12. Yeah, so 12 plus 12 is 24, minus 2 would give you your degrees of freedom of 22. So your t-statistic of 4.66 exceeded whatever critical value there was for t, with a probability level of p less than 0.007. So that was well under the threshold of 0.05 to be significant. So this is how you would write in your report or in your PowerPoint slide. This is how you would report in APA format results if you were to do an independent t-test. Okay, so just to review what we just said. Okay, so now we're going to the other side of it, dependent t-test. So dependent t-test is when we have one person or each person in the group assessed over multiple time points. So a baseline and a post-test. So as I look, a lot of you are doing this type of design, pre and post. So from your textbook, it's an even uglier formula than what we had for independent t-test, but here it is right here. Okay. Just want to make you aware, but we won't actually go in and do that. So there is a formula, but Excel does that for us, thankfully. Okay, so now the other difference. So a dependent t-test is different from an independent t-test in the degrees of freedom. Okay, so for a dependent t-test, because it's one person doing different time points and the same dependent variable, is just n minus 1. So that's the other key difference with the dependent t-test. Okay, all right, so I want just, if we could, just so you can see, I've got everything in here as if we were going to do the whole formula. You can see how much process it would take, but we'll do the automatic Excel function because that's what software is for, right? Okay, so we'll do one dependent t-test. Mid-thigh circumference, pre-squat training versus post-squat training. Okay, so let me just ask you a question. Is this going to be two-tailed or one-tailed? Well, if you do squats, is there a theoretical basis for what? It's probably going to increase, right? So we don't know how much or if it's going to be significant, but it's going to be a one-tailed test because if you're doing squats, you're working that muscle there. You might expect that there'd be an increase in circumference. So it's going to be a dependent t-test with a one tail. Okay, so there's 10 people. So let's take a look at table 5. So tell me what one-tailed, 10 people, what's the critical value of T for that? Okay, so degrees of freedom is 9, right? So dependent t-test n minus 1, 9. So we're going to a one-tailed test. Okay, so I see on here 1 point, yeah, do you see that? 0.833, okay. So it's a little bit different than an independent t-test. So we'll run this one here. So if you want, you can just put the cursor right here in C31, just right next to it here. This spreadsheet is set up to go through the long formula again, which is why you have all this here, but let's just use the quick software. So data analysis, and then remember paired t-test is the same as dependent t-test. So then click OK. And so it's pretty much the same idea. You can put in pre-squat as your title. You're able to post-squat. And you can get your labels and your output. They're right there. And so then you have this nice table, paired t-test, dependent t-test. So you have the mean circumference at the mid-thigh, pre and post. Okay. You have your T statistic, which is right there. Okay. So we can highlight that. Okay, now every once in a while, Excel might come back with numbers in this format, in that exponential format. So I want to teach you how to change that, so you can get something that would be more meaningful to you. So here's how you do it. So you can highlight everything there, and then right click. Okay. So to change the format, you're going to go into Format Cells. So that's just this choice right here, Format Cells. Just like that, and then you'll have some choices here. So change it, you can just, rather than being on General, you can just click on Number. And that will change it to where it's back to where it makes a little more sense. Now, you can also change the decimal places. Why don't we do that? Maybe move it up to 6. You can just click right here and move it up to 6, just a little bit. And then you can click OK. And so now you've got numbers in there that are a little easier to work with and understand. So the next point, you need to take the absolute value of the T statistic. So remember how we did that with effect size? So it's the same thing here. So taking the absolute value of negative 6.64 is 6.64, right? Which is a lot greater than our T critical for a one-tailed test, right? Okay, so we do have a significant result with the exact probability right here. So the exact probability is a lot less than 0.05. So it would be significant at the 0.05 level for a one-tailed test. So Drew, this would be exactly what you'd do for your analysis with a baseline and post-test. You just organize your data like that, and then you have this nice, neat table that you can just stick in your PowerPoint for everybody to see what your results were. So, okay, so let's keep moving. Any questions on independent or dependent t-tests? Okay, so Excel's nice. The key is just to have your data put in the right way, and then makes it really easy. All right, so in summary, you want to use Table 5, so you have that in hand. Decide on the probability level, so usually 0.05. Calculate the degrees of freedom. Okay, so that's going to be different for an independent versus a dependent t-test. Still use Table 5 for both. Read the critical t-value, so you need to decide whether you're running a one-tailed or a two-tailed test. So that's up to you. That's open to interpretation. So your decision on that. Compare the critical t-value to the calculated t-value. So in order to be significant, the calculated value has to be greater than the critical value. Okay. All right, so I want to drift back and talk a little bit about effect size, because effect sizes have a lot to do with the normal distribution. Okay, so do you remember the formula for an effect size? What is it? The Ray formula.
Post minus pre, divided by statistic deviation.
Yes. So essentially what we're doing is we're putting effect size into standard deviation units. That's all it is. So if you get an effect size 1.0, that means you had an improvement of 1 standard deviation, right? And so there's a certain percentage of scores that are associated with each standard deviation, right? So what percentage of scores lie between 0 and 1 standard deviation? Remember from the normal curve, maybe from stats 216? So about 34% of scores lie between 0 and the first standard deviation. So what we can say is that if you have a 1 standard deviation difference, in other words, an effect size of 1 between baseline and post, we can say that there was 34% improvement, because that's the percentage of scores that lie between 0 and 1 standard deviation. So an effect size is a lot like, how many remember z-scores? That's all an effect size is. An effect size is in standard deviation units and is the same as a z-score. So in this case, we've got group 1 and group 2. We could even call this time point A and time point B. So after a period of training, we could say that group 2 has a mean that is 1 standard deviation above the mean of group 1. So we might even say group 1 is the control group. So they had no change. They didn't get the treatment intervention. So you would expect that they would still be at baseline, right? Because they didn't get the treatment. Now, group 2 is up here at 1 standard deviation after the treatment, after the period of time. Group 2 is now has a mean that is 1 standard deviation above where they started. So we can say that's a z-score of 1. Now, if we look at this table, that gives us the percentile ranks, and that's on the next slide. Okay, with an effect size of 1, we can infer that the treatment improved about 34%, because between 0 and 1, you have 34% of scores. So you could say an improvement of this much. Okay, so starting out at the 50th percentile, ending up here with a z-score going from 0 z-score to 1. Okay, you go from the 50th percentile, that's where you started, and now the mean for group 2 is up here with a z-score of 1. The percentile is now 84.13. So going from a z-score of 0 at the start to where at the end of the intervention, group 2 is now 1 standard deviation above where they started. They're going from the 50th percentile where they start to where now, after the treatment, they're 1 standard deviation above, which is 84.13 in their percentile. So we say that would be a 34.13% improvement based on comparing where they ended versus where they started in their z-score. Okay, all right, so analysis of the variance. So this is getting down towards the end of what we're talking about for today. So analysis of the variance. So what I want you to think about, the only difference between an independent t-test and analysis of the variance is more than 2. Independent t-test is 2 groups. Analysis of the variance is more than 2. So now we have more than 2 groups, more than 2 conditions, more than 2 time points. So how many of you have read a study where maybe it was over a long period of time where they might do a pre-test, they might do a midpoint, and then they might do at the very end? So that's 3, right? So that requires analysis of the variance. So anything more than 2 is when we get into this. Okay. All right. So for this part of class, at least today, you're going to be using your F table, and then you're also going to be using this handout right here. So if you look, you have two examples. So labeled at the top, you have example 1. And then on the back, you have example 2. All right, so let's take a look. So this is the output that you would get in Excel. So let's take a look at example 1. Example 1, EMG activity of the external obliques during a barbell overhead press at 50% of 1 RM and 75% of 1 RM on stable ground, and 50% of 1 RM while standing on a BOSU. Okay, so we have 3 different conditions. Okay, so the dependent variable would be activity of the external obliques. The independent variable would be overhead press. And how many conditions does overhead press have? 3. Yeah, so 3 conditions of the independent variable, all looking at activity of the external obliques. That'd be your dependent variable. Okay, so don't do this at this point. I'm just showing you where it's at. So you put all your data in like before. So here's your participants. Okay, so you don't need to pull this up. I'm just showing you how it would go into Excel. So you have your conditions right here. So this represents the activity of the external obliques as a percentage of maximal voluntary contraction. So if you've had kinesiology, you take EMG data as a percentage of max. So this represents, for example, participant 1 for the overhead press at 50% of 1 RM had an external oblique activity of 15% of a maximal contraction. So going across, so participant 1, participant 1, participant 1 for each condition 1, 2, and 3. Does that make sense? Good? Okay. All right, so where do you find that? Well, you would just go here. And so the choice that you'd want to make would be ANOVA single factor. So single factor means 1 independent variable. So that'd be the overhead press is 1 independent variable with 3 different conditions under that. So conditions that's why we're doing an ANOVA, but it's still just 1 single factor, which is the overhead press, with 3 conditions under that factor. So that's how you would run it. But for now, what I want you to look at is this table. Okay. So the output you see is right on the bottom here. So ANOVA single factor. And so looking at this, the first thing you have would be the average scores. So the percentage of EMG activity for each condition. So overhead press, 50% of 1 RM. The average was 18.60. Overhead press, 75% of 1 RM. Average was 33.6. Overhead press, 50% of 1 RM on a BOSU, 26.51. So does everybody see where I'm looking to get those numbers there? Okay, so that simply just gives you the average across 8 participants. So there were 8 participants in this particular study. Okay, so now going below that, you have a couple of numbers that you want to be looking at. They're all found right here. So there's your F. So rather than a T statistic, you have the F statistic, okay, or it's called the F ratio. Okay, you have the p-value. Okay, right there. So p-value of 0.039. So do we have significance? Yeah, somewhere. Do we know where? No, we really don't yet. We will. Okay, we don't know if it's between condition 1 versus condition 2. We don't know if it's between condition 1 versus condition 3 or between 2 and 3, right? So all that p-value does is tell you that you have a significant difference somewhere. So the next step would be what's called post hoc's. Post hoc's or pairwise comparisons, which is where you determine where the significant difference is. Okay, so this is just step 1. Okay, and then the F critical value. F critical value right there on the very end is 3.4668. Okay, so let's talk about where that critical value comes from. If you look to the third column, there's some degrees of freedom listed there. Okay, so right under degrees of freedom, you see the 2, okay? And then right under that, you see 21, okay? All right, so let me show you how that number, how we got that number, and then I'll show you the reason why, okay? So take your F table, and so you're going to find 2 different degrees of freedom and match them up. The first thing with this F table is that all of these critical values correspond to the 0.05 level. So we don't need, like with table 5, how we matched it up to the probability level. You don't need to do that with the F table, because every single value in this table corresponds to a probability level of 0.05. Okay, now, one more thing about this table is the 2 represents the degrees of freedom for between groups. So if you go over, okay, so you have 2, and then you go across, right here, that represents the degrees of freedom between groups. Now, I'll explain what that is in just a minute. Okay, just remember for now it's between groups. Okay, the other one is 21. Okay, that represents the degrees of freedom within groups. Okay, so just remember that for now, and then I'll explain why. Okay, so for between groups, I want you to go across the top and go to the second column where it says 2. So that's the first place you need to be. So across the column where we have 2 degrees of freedom for between groups. Okay, now from there, I want you to go all the way down to where you get to 21. So you're matching up 21 on the left with 2 up above and going down. And so what number did you come up with? Yeah. Yeah. So, and then if you look at the critical value here, okay, it's the same. So that's where that comes from. All right. So let's take another step and talk about how this works. So single factor ANOVA, just like what you have in front of you here. Okay. So the textbook is great. It always presents the long method. Okay. We're not going to do the long method. Okay, that's what we have the software for. But just so you know that there is a source for all of the equations within the software. It's called the ABC method. And so table 9.2 in your textbook takes you through all of these steps, and it takes a long time. Now, look at the table that you have in front of you, and I want you to compare it to how this table looks right here. You see that the columns are pretty much the same, The rows are labeled the same, right? Okay, so all the numbers that you have in this ANOVA table that we generated just like that automatically, this is where they come from using this ABC method. Okay, so just so you know where these numbers come from. But we have the software so we can generate all this really fast. Okay, so between degrees of freedom, K minus 1. Everybody see that? Degrees of freedom for between is K minus 1. K is the number of conditions. Okay, so we had overhead press with how many conditions? 3. So number of conditions minus 1 is 2. So we have between groups, our degrees of freedom is 2, just like you see there. So the automatic output, really nice. Okay, so degrees of freedom within groups is N minus K. So we know K is conditions, N is the total number of observations. Total number of observations. So if we had 8 people that did 3 different conditions, how many total observations do we have? 24. So 24 minus the number of conditions is what? 21. So that's where this number comes from. So where does the F ratio come from then? The F ratio comes from the ratio right here with the column header MS. MS stands for mean squares. Okay, so basically we're taking the variability between groups and dividing it by the variability within groups. Okay, so if you have a group of 8 people doing 3 different conditions, ideally what you want to get a high F ratio is a lot of difference between conditions, right? So F ratio is between differences on top, within differences on the bottom. So between differences on top is the differences in how people respond to each condition. So the idea is to say, okay, well, we want lots of difference between these conditions, right? So we want lots of difference between condition 1, 50% on stable ground. We want that to be different from condition 2, 75% of 1 RM on stable ground. And we want that to be different from condition 3. So we want people to respond distinctly to each of these 3 conditions. That's the variability or difference that you see here between groups. So that's the number right here. So it's 450 mean squares. That number represents the overall difference between those 3 conditions. So we want that number to be really big. So 450.8 will round up 450.86. Okay, so what's the number in the bottom of the ratio? That's the differences within each condition. So if you have 8 people doing 3 different conditions, you want very little variability within. In other words, you want numbers to be very similar within condition 1. You want numbers to be very similar within condition 2. And you want numbers to be very similar within condition 3. So you want small differences within, but large differences between. Okay, so if the F ratio is a ratio of differences between conditions, divided by differences within conditions, how are you going to maximize that F ratio? How are you going to get a really big F ratio? You're going to have a really large number on the top, right? So lots of differences between, but then a smaller number on the bottom, right? So very little differences within each one. Now I want you to take a calculator and I want you to divide 450.85. That's the overall differences between conditions divided by 119.03. Okay, so that's where your F ratio comes from. So the greater the number on top, representing differences between conditions, the smaller the number on the bottom, representing differences within, means you're going to get a very high F ratio, which increases the chances that your F ratio is going to be greater than your critical value that you get from your table. And so if your F ratio exceeds your critical value, then you know it's significant at the 0.05 level. So this gives you the exact probability, and it was way under 0.05. Okay, so knowing that, the very next step is what we call post hoc comparisons. So post hoc comparisons, where we determine exactly where that difference is. So post hoc comparisons that we'll get into on Thursday, we compare 1 versus 2, 1 versus 3, and 2 versus 3. So it's very similar to t-tests, but you have to do this part first to see if you have a significant difference somewhere. And if you do, that's step 1. If you do less than 0.05, then you can take it a step further and do comparisons between conditions to find out where that significant difference is. So that's a lot. Do you have any questions? So we're gonna keep pounding away on this. In fact, example 2 we'll get to on Thursday. So if no questions, thank you very much. Please don't lose these papers. Let's just pick it up right here with ANOVA on Thursday. Thank you.